Thank you for the introduction. It's a real pleasure to be here. I think it's my first scientific visit to Milan, and probably not the last one. I will talk about this topic, unique continuation for Schrödinger equations, and my plan is to cover two things. We'll see if I will be on time to do both. I will talk about Landis conjecture first in a very general terms, and this is what I plan to spend more time on tomorrow and give you some details of the proof. But since it's a more general talk, I would like to spend the second half of the talk on something lighter and show you a nice proof of Hardy uncertainty principle, and then show you how it's connected to Schrödinger equation and mention some open problems there. The talk is based on two works. The first part is a joint work with Logunov, Nedirashvili, and Nazarov, and the second part is joint work with Fernandez, Bertolin. So let us start slowly with the first part, and this is the setting. We look at the Schrödinger equation with bounded potential, no time, just Laplacian u plus v is equal to 0 in R2. Potential is nice and bounded. And in 60s, Landis asked, do we have solutions to this equation that decay faster than exponential? He asked the question in any dimension. Why exponential decay? Exponential is something that is very easy to construct. If you just take the exponential function, you see that the ratio of the Laplacian to the function is bounded. Probably, as written, is not very well defined near the origin, but you can always modify it near the origin and have a solution with bounded ratio of the Laplacian over the function that decays exponentially. Also, if you assume that your function is positive or negative, doesn't change sign, then the decay is not faster than exponential by the Harnack inequality. If you take two neighboring balls of radius 1, the ratio of the function is bounded by some constant, by Harnack, and then you can go to infinity and you see that the decay is at most exponential. I'm not sure what was the motivation for Landis, but some years later it was revived by the following considerations from the spectral analysis. If you have your Schrödinger operator and you look at eigenfunctions, there is a nice, beautiful results of Agmon saying that your function should decay exponentially if you go in the forbidden region where the potential is larger than the energy level. Think about the harmonic oscillator. I'm looking at some eigenvalue. I know that when I'm in the region where my potential is larger than this eigenvalue, the function should decay exponentially. And the question is how precise this Agmon result is. For many examples, we know that it's precise, for many physical examples, and I think some belief in physics community is that this is the right exponential decay. So they would be very happy to learn that Landis conjecture is correct, and there is no eigenfunctions for bounded potentials that decay faster than exponential. And I'm going from bounded to harmonic oscillator, but you can see that this, if we can solve the Landis conjecture in any dimension, we can show that for reasonable potentials, there are no eigenfunctions that decay fast enough. I will give you one proof of a very simple bound that there is no function that decay faster than Gaussian. There are no solutions to this equation that decay faster than Gaussian. This is far from the original question, but it uses one of the tools that we will see later as well. And the tool here is a Carleman inequality that tells you that if you have any functions with compact support, say C infinity function, then its L2 norm of the Laplacian with the Gaussian weight is larger than L2 norm of the function with this Gaussian weight. And you have also a coefficient that grows with this constant. I have t squared when I have t here. This is a simple of Carleman inequalities with very large growing weight. And if you believe in this inequality, and you have an eigenfunction here, you multiply eigenfunction by some cutoff to have a function with complex support, apply the Laplacian, you will have this part and the part that leaves only where your cutoff is not a constant. And this part, if you put this integral here, will be smaller than this if t is large enough, larger than the norm of the potential. And the cutoff will be small if you assume that your function decays fast. And then this inequality will be violated. So this Carleman inequality applied to solution to the Schrödinger equation multiplied by a cutoff function easily tells you that there is no function that decay very fast. But this is quadratic decay, and we want to know if there is something of a linear decay here. And in the 90s, there is a work of Mishkov who proved that in any dimension, if you have a solution to this equation, it doesn't matter if potential is real valued or complex valued, your solutions decay not faster than e to the power minus absolute value of x to the power 4 cells. His proof is another Carleman estimate, and the proof is, as soon as you have the Carleman estimate, is a simple application in the same spirit as we had before. But moreover, in dimension 2, he constructed a counterexample to original Landis Conjecture and constructed a function that decays with this property with now a smaller constant c, satisfy the equation. But the thing is that the function and the potential are complex valued. Complex valued allows you to rotate the function without having any zero set. So there is a big difference between real valued solutions and complex valued solutions. Real valued solutions, as we know, should have some zero sets because functions of constant sign cannot decay faster than exponential when they satisfy this equation. But for complex ones, you can get around the zeros because real and complex parts will have zeros in different sets, and you will construct a function like that decays fast enough and for which the ratio Laplacian over u is bounded. It's a construction by growing annuli. We showed that you can glue up some nice powers of z, negative powers of this out such that the function will decay fast, but this ratio is still bounded. Before we go further, we'll do one more result. So this is for Koenig. It's now 15 years after the Mishkov. They wanted to look at the solution to the same equation. It just wrote it as an inequality, since we don't know anything about the potential except the fact that it is bounded. And they proved a local version of the result. So suppose that we have a function that is bounded, say the maximum is at 0, and we go away from 0 at distance r. Now we'll look at the unit ball over there, and what Bourgain and Koenig showed is that there is an estimate from below in this unit ball. It's almost the same result as Mishkov. This is r to the power 4 thirds, but since you want things locally, you pay extra price of the law. So your function, if it's bounded, or instead of bounded, you can think that it doesn't grow faster than an exponential, it should decay in any direction. As soon as you have a ball far enough, the should not decay fast and could not decay fast in any direction. Because we know that it's bounded, or the growth is bounded by exponential. For example, if you have a harmonic function, bounded harmonic function is just a constant, but if harmonic function doesn't grow faster than exponential, it cannot decay too fast in any direction. If you want to decay really fast, even on a strip, you will pay a price by growing in another direction. Once again, what is the proof of organic result? Kerr-Lehmann inequality. And this Kerr-Lehmann inequality is like that. So you have here something that looks like absolute value of x to the power minus t. And you're saying that with this weight, the L2 norm of the Laplacian is larger than L2 norm of the function. Roughly speaking, the weight is absolute value of x to the power minus t. If you do just absolute value of x to the power minus t, you can prove this inequality by writing expression in spherical harmonics, look at each mode, and you will get a factor t here. But the nice thing is if you modify your weight a little bit, make it like a convex weight, you will get t cube here. And this cube is what gives you 4/3 in the Mishkov and in this result here. So once again, after you have this inequality, the proof of organic result is quite simple. Once again, take your function, do the cutoff in the right way, and you will get this one. The difference with this inequality with one that I had before is here I should specify that my function is not only compactly supported in the unit ball, but also vanishes at 0. Because the weight I'm writing here is singular at 0. I'm writing something like absolute value of x to the power minus t. So I also want to know that this function is 0 at around 0. But the thing that happened after the work of organic is that they found out about the work of Mishkov and basically were trying to advertise the Landis conjecture, starting from their work, saying that it's related to question of localization of eigenfunctions. So the work was not about the Landis conjecture or this thing. It was a tool for them to prove that if you have a Schrodinger operator with random potential, and what is important that now the random one is a combination of bumps with 0 ones or ones minus ones, something that you can switch on and off. So-called Bernoulli-Anderson model, that you have localization of eigenfunctions near the bottom of the spectrum almost surely here. When you look at the model like that, but you allow this potential, this coefficient to be continuous, say uniformly distributed between -1 and 1, or between 0 and 1, this is much easier result because you can move around this regime switching off and on in continuous way. And you can show that almost surely you have a nice control of your potential. But this result with potential that is just 0, 1 or -1, 1 is more difficult. And they needed the result on the localization of eigenfunctions or properties of the solutions of this equation plus the energy to prove the Anderson localization result. Most of the potential that we want to understand in real life are real valued, so they were asking if there is a better estimate than that one if you know that the potential is real valued. And in particular, can you prove that the Landis conjecture if you assume that not only this inequality is true, but also that the function itself is real valued. It's the same, right? And the idea is that for results like that, Kerr-Lehmann inequality should not give you the difference. The Kerr-Lehmann inequality does not care if your function is real valued or complex valued. If you have an inequality, you applied it for real part and imaginary part, you have the same inequality for complex valued functions. So looks like there is no Kerr-Lehmann inequality that can help you to answer the question for real valued potentials. So starting from their work, there was some activity to understand what happens to solutions of this equation, say in dimension 2 to start with, when the potential is real valued. Solution is real valued. And following the conjecture of Landis and the result of Koenig, you want to ask if something like that, the local version of it, is true. So instead of saying that my function doesn't decay faster than exponential, I'm saying that locally, if I have a function that does not grow faster than exponential, locally, in each ball of radius 1 at distance r from the origin, the supremum of this function is exponential up to this log term here that we saw in the 4/3 case. The difference between the original question and this question is that this question makes sense for potentials both positive and negative. For the original question, when I assume that my function decays, the question doesn't make any sense if I choose the wrong sign of the potential so that I have maximal principle. Right? So there is only one sign of the potential. When it is positive, that could create decaying solutions. And there is some previous work on this direction. For positive, also with some drift term, you have this inequality. For positive is some variable coefficients instead of the Laplacian. Two terms, but this part is decaying exponentially, you still have the result and so on. So there was a belief that in dimension 2 at least, the Landis conjecture should be true, and we should be able to prove both the decay cannot be faster than exponential and the local version like that. And our result is almost this. We're saying that if we have a real valued solution to this equation, potential is bounded, no restrictions on the sign or other size of the potential except for that it's bounded by 1. Then there is no solution that decays faster than e to absolute value of x times square root of the log. And if you want to do the local result, you will have to multiply your estimate by extra log, and here is the local result as well. I will try to explain why we can do it only in dimension 2. And it looks now that probably we don't believe in any version like that in dimensions larger than 2. I'll explain where this square root of log comes from tomorrow. But today I can mention that there is an example that exists in a draft, which is difficult to read to anyone, and I'm not sure that the authors want to publish it at any point, because it takes lots of time to make it publishable. But there is an example of function that satisfies this equation and behaves like that. So the example shows that this square root of log is not the technical issue with our proof, it is there. But I don't know any simple or nice example that you can explain in a reasonable time for function like that. But the idea is that this log is not something from the proof, it's a real issue. I will describe some ideas of the proof, and as I said, I'll do some technical details tomorrow. But the first idea is we want to use the fact that our solution is real, and to do that we will look at the zero lines, or zero things. We were in dimension 2, so there's some lines where a solution is equal to 0. We will, in addition, create holes. So we'll take any domain where the solution has some sign, positive or negative, and create extra holes in this domain. The idea of creating these holes is that I want to construct a solution of the equation w phi plus v phi is equal to 0 with that is very close to 1. I want a solution to this equation phi that I can control. And we know that if I, for example, do it locally, take a large ball, try to say my function is equal to 1 on the boundary, I try to solve the equation. There is no solutions to this equation because, I mean, there is not uniqueness. Here, we want to make sure that our domain has a small Poincare constant, or that the first eigenvalue of the Dirichlet Laplacian is large as for a small ball, to make sure that we can solve the problem. And we are doing it by creating extra holes and changing the first eigenvalue of the Dirichlet problem for the domain. It's one of the things that we will discuss more tomorrow. But the idea is that you can construct a positive solution that solves the equation and then look at the ratio. What do you win? You get rid of the potential. As we teach in the calculus class for the ODEs, when you have two solutions, you look at the ratio of those and you get something nice for the equation for the ratio. So we get rid of the potential, but we pay a price, and price is that now our equation is like that. We have coefficient in front of the gradient. So it's a divergence form, second order elliptic PD with this not very regular but kind of almost constant function phi that we want to consider. And another price that we're paying is that our solution is not solution in the whole plane, but in plane without holes. One thing why we used the zero set to start with, we had zero sets and we created holes far from the zero set. And the idea is that then those holes are not so bad because around each hole, your solution has sign, is a positive or negative. So you have a solution of this equation with annoying coefficient in the whole plane minus the union of balls, and the behavior near the balls is nice because you have a solution to the divergent type equation with some sign, so your solution is as Harnack function. You control the ratio between the values and you control the gradient near each ball, so the behavior near ball is not bad. And on the boundary of the ball, the function is 0 because your function u was, no, sorry, it's 0 on the nodal lines, but not on the balls. This first step, it has some two-dimensional features, but probably you can do it in higher dimensions as well. The construction and the solution of the Dirichlet problem is something you can do in any dimension. Computing the Dirichlet constant of a domain is easier in dimension 2 than in higher dimensions, but still it looks like you should be able to do something like that. But in the second step, we will use the fact that we're in dimension 2 a lot. And you can guess if you have an elliptic equation in dimension 2, you know that you can do change of variables to make it Laplacian. So we'll do the quasi-conformal change of variables to make the function harmonic. You need to do it carefully on some scale, choose the size of the holes in the right way to get to a toy problem. And here is a toy problem. In dimension 2, you have collection of disks, all of the same radius. They're far from each other. Function is harmonic, and we assume that near each disk the function has the same sign. So the 0 set doesn't intersect this annulus around this. Then we claim that the function cannot decay faster than exponential. To be honest, it took us some time to understand this problem. After it's understood, I think it's a nice exercise in complex analysis to good undergraduate students. But there is nothing there except the maximal principle for analytic functions. And I'll try to explain it tomorrow. So there is nothing difficult there. I mean, when you believe in it and you know how to prove it, it looks very elementary. There is elementary proof of it. This last step, if you do the same game in high dimensions, once again, there is Riemann inequalities. And you can use this information that there is no zeros around each pole to play Riemann inequality. And what we can do in high dimension is that if you allow yourself to lose a log here, you're good. So for the third problem in high dimension, there is a version of it by adding an extra log. But as I said, the main thing is that step 2 is very two-dimensional. There is no reasonable substitute for this quasi-conformal change in higher dimensions. And there is a counterexample to Landis in a cylinder, not in the whole plane, but in the high-dimensional cylinder by Filonov and Krimsky. I think it's from a couple of years ago. They first gave example in half cylinder, then in the cylinder they have a solution that decays exactly as the Mishkov example. And I think their belief is that it's question of time and refining of the technique when they will upload the solution for the Landis conjecture. But when you have at least 3 dimensions, you can play now not with a real and complex part, but with changing the frequencies of your function in different directions from one layer to another one to construct a counterexample in higher dimensions with this rate. I probably should have some of the time recorded and not say too much, but so this is the status of the Landis conjecture up to the square root of log that seems necessary. There are no functions decaying faster than exponentials dimension 2, and plausibly the ones in dimensions starting from 3 is very different, and there are others. And then the real question is, if we go back to the question that physicists are interested in, with eigenfunctions of reasonable physical Schrödinger operators, what makes eigenfunctions decay exponentially and not faster than that? Are there any conditions on this V that will give you something with it? As far as I know, we don't have any reasonable, except for decaying V or something like that, we don't have reasonable situations where we just think that this is bounded potentials where we know that eigenfunctions don't decay faster than exponentials. Would expect that there are probably some results for most potentials if you look at some models, something like that, but I don't think that deterministic results are nice at saying that the functions decay as we expect them to decay by diagonal distance. So I will stop here about the Landis conjecture, and I'll give you some details tomorrow, but if you have any questions right now, this is a good time to ask.
I don't know if it's maybe you can do explore a bit later, but can you give an intuition for why exactly 4 the plane, which sounds weird?
No,
Okay.
I don't have intuition for that, but if you do the exercise and you use this Riemann inequality, you will get 4/3. It's very natural from here.
Yeah, it comes from.
Yeah, it's 1 minus 1/3 or something like that, or 1 plus 1/3. Yeah, but this is, if you try to use this inequality and say what rows you can forbid, you will see that you will need this for such, but I don't have intuition why this is the right thing. But it looks like it's the right thing, and it would be nice to see that. But I don't know if the examples are physical. There are some examples, but what are they? Some bounded strange function that you can construct. Maybe the assumption that V is just bounded and no other information is not very physical. I want to switch here and tell you, I don't know, toy story. I'll start with a toy story. And at the end with why we started to think about it. But the toy story is the following. Let us look at the Schrödinger revolution now. Forget about potential and think about solutions to Schrödinger equation in time. Now your function depends on time, and you have something. And you ask how the solutions of this equation can decay in space. And by that at zero moment it could be what you want it to be, some initial condition. Then you will look for Schrödinger evolution and you ask what will happen to it after some time. And the question is, suppose that we have solution to the Schrödinger equation that decays fast at two different times. Can you say that the function is, do you have some uniqueness like that? Once again, I think the people who are doing real physics, there is no sense in measuring solution to the Schrödinger equation 2 times. The first time you measured, you ruined everything. But from a mathematical perspective, it's a reasonable question. Suppose that this is evolution, the initial condition decay, and then it decays also at some other time. What does it mean? And we will see that it's just Hardy uncertainty principle that tells you that there is no way it will decay very fast at the times. Very fast as one Gaussian with some right coefficients. This is the slide about the way how we solve the equations. We know that the solution of the heat equation is a convolution with heat kernel. I think all of us know that by heart. And then what is the solution to the Schrödinger? You can work with something that you will get when you change time to I times time. And I'll go back to this idea that actually we have one heat kernel, but we can use it with time that is not real. Why not? This is a nice function. I mean, it's not so nice as the Gaussian doesn't decay, but if I have a nice initial condition, I can convolve my initial condition with this function and get solution to the Schrödinger equation. So if you do this and you will start playing with the Schrödinger evolution, you have your initial condition, you see what happens to the when you convolve with this one, and if you look here, what happens when I convolve with this one? I take my initial condition, I multiply it by some function that is complex Gaussian in y. I do the Fourier transform, and I multiply with something like that in x. So going from one time to another one, there's 3 iterations. You take your function, you multiply by something of absolute value 1, that is e to I absolute value of x divided by 4t. Then you do the Fourier transform, then you multiply once again by something of absolute value 1. So if I have 2 moments of time where my function decays fast, then function multiplied by the exponential complex Gaussian decay fast. So you have function and its Fourier transform that decay fast. And we know by Hardy that there is no functions that decay fast like that. Function and the Fourier transform really faster than the Gaussian, say 1/2 Gaussian, if I normalize my Fourier transform directly. And now the question is, if you want to understand the proof of the hard uncertainty principle, what should you do? If you look at any book, I think most will do it using complex analysis and using Friedman-Lindelof theory. If you go back to the origin and look at the hardest paper, he gives two proofs. In his original paper, he gives two proofs of hard uncertainty principle. One that makes its way to all the books using Friedman-Lindelof theorem that basically maximal principle with smart multiplication by nice functions. And there is another one that I don't think any textbook repeats. But I will explain you why I like the other one. I will give you a proof of the hard uncertainty principle. I will cheat a little bit and I will give proof exactly what is written here. In hard uncertainty, when variances are 1/2, you also know that it's Gauss. It's a bit more complicated, but not much, the second part of it. And I will do it using Schrödinger revolutions. So I'm saying that the hard uncertainty principle is just equivalent to this statement about the Schrödinger revolution of 2 time, and I'll try to give you a one-page proof of this result that uses some facts about analytic functions, but only the fact that if you have a bounded analytic function, entire function is constant. So what is the idea of the proof is to think that we have heat kernels for complex variables. And I have some initial conditions, I can do different things. If I can work with the heat kernel itself, I'm solving the heat equation. Yeah. I would prefer to have a drawing, but you can have it in your head. You have a complex plane. If you go along the real line, you solve the heat equation. When you go along the complex line, up or down, you're solving Schrödinger, either backward or forward. Schrödinger, they're the same. It's very difficult to go back in real line because you're trying to go for something that grows very, very fast with Gaussian, with very, very good coefficient, so there is no way to solve the backward heat. But suppose that your initial condition is reasonable or is nice. Suppose your initial condition is like that. Where can you solve your equation? Where can you convolve with it? And this exercise definitely in undergraduate calculus to see that you can convolve when z is any point except for a disk that touches the imaginary line at the origin. And I can define this function, this convolution, everywhere except for this disk. It will solve the heat equation on the real line. It will solve my Schrödinger and the imaginary line. What is the physical meaning of going around the circle to the negative time? I don't know, but I don't care. It's a nice function. But now what I am given is that when I solve it along the imaginary line, go some time along the imaginary line, I'll again get something of this sort. So I can start from this point and convolve it with this one. I'll get another function that is defined everywhere except another disk that touches the imaginary line once again. And they will be the same thing. They will be the same thing along the Schrödinger revolution, the holomorphic function, they will be the same thing everywhere. And the case of the Hardy uncertainty principle is exactly the case where those disks don't overlap. So by convolving my initial condition with this function and using that, I know that at some point in the Schrödinger revolution, it's also decaying fast enough, I created something that you can extend over the complex plane. If I'm on the critical case of the hard uncertainty principle, there will be one point where I have a pole, and you have to analyze this pole. But if I'm in the regime where there are no solutions, I will have something analytic everywhere, and you can check that if you fix one point and look at this function, this is bounded function. Bounded analytic function that is now defined everywhere, so it's a constant. And if you look at the transformation that Hardy is doing in his second proof of the Hardy uncertainty principle, it's very similar to the transformation that you see here. He's not doing it in these terms, he's not doing it in terms of the evolution of heat kernels, but he's doing it using the integral transformation that is very, very similar to this one. So this is fun story. More seriously, this is the question that was considered some years ago by Skuriaza, Koenig, Ponce, and Weger, and they looked at the evolutions with potential. Potential is allowed to depend on time as well, so you can include nonlinear Schrödinger solutions to nonlinear Schrödinger equation. You assume that potential is nice. For them, nice is bounded, real valued, and there is some decay at infinity of the potential. And then they show that exactly the same uncertainty principle holds if at 2 times your solution decays faster than the Gaussian, then the solution is 0. And it took them, I think, 3 papers to go from twice this number to this number. Twice this number is much easier, and you can do it in 1 step. To go to this number, they need, in a sense, in many steps. They need very nice iterations of their scheme, but at the end gave them the right result in the end.
Out of curiosity, sorry, is it the same idea? Can you use the same idea as before? No, of course, it's
Unfortunately, no. Unfortunately, you cannot. I mean, even if V doesn't depend on time, then you can have some hope of using the same idea, but we don't know how to think about the kernel in the right way. How to do it there. But we're playing with the same problem for situation where instead of Laplacian, we think about the discrete Laplacian. So you have a discrete Laplacian, and you want to know what happens if you have solution to this equation with, I would say, just bounded potential, how fast it could decay. You start with assuming that there is no potential at all, and what is the right decay at infinity? Is it Gaussian or non-Gaussian? What is the right decay 2 times for this equation that guarantees you the limit? And very soon you realize that there is no Gaussian decay there. What you have to compare is the heat kernel. And this heat kernel behaves as a basic function. And for the case without potential, we know that if there is a solution that at 2 times decays fast enough with a particular constant here, then the solution is 0, and if this constant is the exact constant that corresponds to basic functions, we know that the solution is the basic function. So the story about the free Schrödinger is the same up to the fact that you have to replace the Gaussian that is heat kernel by the discrete heat kernel that has a bit different decay. And what we were able to prove with Gero is that you have something like that when you allow yourself bounded potential, but our constant is not the one that we have in the free case, and we don't know how to fight for the right one. So we were sitting with this problem for some years. We know how to do a large constant here. We believe that the constant should be exactly the same as for the basic functions, but we don't know how to get there. Maybe this bound is not the right one when we think about the evolutions with potential. In the continuous case, there was some decay. Here, there is lots we can do for bounded ones, but I don't know what the right thing. And somehow, surprisingly, when you go to the discrete world, the size of the potential makes a difference. When the potential is very small, like, I don't know, 1/1,000,000, this is a small term compared to the Laplacian. But when potential is large, it competes with the Laplacian on the equal terms. The Laplacian is nice bounded operator. This is bounded operator. It's not clear which one of them is the most important. So I would say that we can do it for any constant here with another constant there, and maybe this is not the right model, and we really need to think about very small potentials that are like small compared to the Laplacian in the discrete world. I will stop here. This was our explanation why I was interested in the Hardy uncertainty principle, and I think it's unfortunate that we forgot the second proof of Hardy. Thank you for your attention.
Any question or comment for Eugenia Malinnikova?
I think you talked, when you talked about the cylinder case, you said something about your expectation about the conjecture and the dimension.
Yeah.
So you expect it's false?
Yeah. I expect that the example should be
Global dimension.
yeah, with some technical things maybe done to get a counterexample in RT as well.
So one could consider also the discrete version of the Landis conjecture then?
It's a question how you formulate it, because in a way there is no, if V is small, and this is a small perturbation of the Laplacian, there are no function that decays faster than the exponential. It's easy to see. So there is a version of the Landis conjecture that is simple for discrete functions. There is no room for them to decay faster, in a sense. There is only, yeah. I mean, very roughly, you know that your function is, I wouldn't say out, but yeah, there is no room for them to decay faster than exponential in all directions. It's a local thing. But maybe there is another correlation that is more relevant to that.
Any other questions? If you don't mind, I'm embarrassed to say, can you go back to the quick proof of the uncertainty principle?
Yeah.
What about why, can you give an idea for why you can convolute outside of that circle?
I'm just writing, so this is my kernel, right?
Yes, exactly.
I'm writing what does it mean that the real part of 1/4 was Z
You just need
is
enough decay.
less than alpha.
Okay.
Right? I just compare this exponential to that one. There is a real imaginary part, and I'm writing the equation that the real part here is not larger than the alpha here. Yeah.
Okay.
And you get the equation of the circle.
Easy.
Yeah, easy. Yeah, it's easy. I mean, I don't know what it is, but formally you can convolve. And it's the right thing over this axis, and there is something else, but there is a function depending on z and x that